So we are going to continue for the next hour with further presentations. The next one is from the Machine Tool Laboratory from the WZL Aachen. And the contributors are Christian Brecher, Stephan Wein, Xiaomei Xu, Simon Storms, and Werner Herfs. The paper is entitled Simulation Framework for Virtual Robot Programming in Reconfigurable Production Systems. We are looking forward to your video presentation.
Hello, my name is Stephan Wein and I'm working at the Laboratory for Machine Tools and Production Engineering at the RWTH Aachen University. In this presentation, I'm going to present to you my research work on the Simulation as a Service framework for virtual robot programming in reconfigurable production systems. First, let's think about why do we need virtual robot programming? In the industry, especially for small and medium-sized companies, the robot programming by teach-in is still state-of-the-art. And because it requires expert knowledge, it is not suitable for non-expert users. Thereby, the translation to other domains, like biolaboratory work, is slowed. Other approaches allow easy-to-use robot programming by guiding the robot manually. This is especially used when programming robots for human-robot collaboration. However, when having a flexible reconfigurable production system with a higher number of changes, this type of programming exceeds the range of efficient usability. Virtual robot programming can close the gap by anticipating certain activities. Depending on the maturity level of virtual commissioning, the effective cost of commissioning can be reduced significantly. Now let's take a look at an exemplary reconfigurable production system. In one of our research fields, we are focusing on lab automation. A central demonstrator is the iCell Factory, a reconfigurable automated production platform for stem cells. The system consists of a base system and 3 positionable modules for laboratory devices. In the following, the system is used as an exemplary use case to demonstrate the functionality of the framework. What happens when the plant's physical configuration is changed? We need to update the virtual environment. Modules or components can either be removed, added, or modified. But how is it done? Different sensors can be used to measure objects' positions in a three-dimensional space, for example via vision systems. The measured position, orientation and the object's ID are then written into an asset administration shell, which are instantiated for every module registered in the data management. The asset administration shell also contains a watchdog system, allowing the recognition of parameter changes. In case of changes in position or orientation, the shells actively request a simulation service, providing all relevant data to it. After the robot path planning is done in the simulation, the paths are written into the respective asset administration shell again. There, the control system can access the information and execute certain robot operations. The paper related to this presentation focuses on the simulation as a service approach. Our proposed simulation framework is based on a service-oriented architecture. To structure and modularize the simulation, it is split in main services and sub-services. While main services always host sub-services, the specific set of these sub-services can be changed on runtime. Thereby, the simulation can be adapted to the needed requirements. For example, a sub-service to ensure safe transport of open liquid vessels can be included. To support this adaptable framework, a method is required to combine different sub-services. By defining a so-called pre-service description for the required data of a sub-service, and a post-service description, returning the resulting output of a service, multiple services can be linked. The service description can be semantical and/or numerical. For example, a subservice for composing the virtual cell requires a kinematized CAD model. This requirement is defined in the service's pre-service description. Another subservice, preparation of models, returns these models as a result. This information is captured in its post-service description. The final information set is also given as the post-service description of the respective main service. Now let's take a look at some selected subservices of the framework. In order to set up the virtual environment, prepared module models are required. Therefore, the CAD models of the modules are extended with oriented vectors, defining collision spaces, interaction points, search points, and initially the position of modules matrix code. The collision space vectors are later used to reduce the model's complexity while simulating, reducing processing time. Interaction points define the positions of modules for objects manipulated by the robot. To reduce the amount of possible robot paths and enhance the algorithm speed, search points can be defined. For modules with an internal kinematic, internal axis can be defined, allowing an extended collision check. Models prepared with the subservice are saved within their corresponding asset administration shell and can be requested from other subservices. For example, when setting up the virtual environment. For path planning, we propose a subservice divided into 4 process steps that are processed iteratively. First, the start, search, and endpoints are checked for validity. All points must be reachable without any collision in a static pose. In later iterations, all the intermediate points are checked. In the second process step, a path planning algorithm based on rapidly exploring random tree searches for nearest neighbors using KD trees. Then the intermediate points are interpolated, and the movement is checked for collisions. In case of a collision in the movement or condition validity check, the interpolation's intermediate points can be reused for setting up the path. The transport of open liquid-filled vessels via a handling robot is an important application in lab automation. To demonstrate the adaptability of the framework, 2 different but combinable subservices to avoid spilling liquid are used. The first one utilizes the adaptation of the TCP's rotation. Spillage depends on multiple parameters, for example, the acceleration. As the literature describes, liquid can be modeled as a pendulum. The acceleration is proportional to the displacement angle, and spilling liquid can be avoided by correcting the TCP's rotation angle depending on the acceleration profile of the TCP on track. The second subservice concentrates on the rotation angle of the TCP and its dependencies from the robot configuration. Thereby, the rotation of the TCP is not fully inhibited, but restricted to a limit of 10 degrees in maximum. As you can see, different robot configurations result in varying robot paths with different rotation angles of the TCP during movement on the paths. The orange lines show the movement from one intermediate point to another. When the line is red, an additional collision has occurred. The goal is to find the optimal configuration for each path and ensure a safe translation between different robot paths. Once the optimal robot configuration is found, the full path has to be checked for collisions in the movement again. A combination of the 2 subservices can achieve even better results in avoiding spillage. but also reduces the number of possible paths, as additional collisions have to be checked. The evaluation of the subservice indicates its usability for the application, as the rotations around the TCP's X and Y axis show only slight deflections for multiple different paths planned with the algorithm. In this exemplary path, the deflection is underneath ± 10 degrees. Stable robot path can be achieved using the subservice. Let us make a short conclusion. The usability of the simulation framework was demonstrated for an exemplary reconfigurable production system. Also, the framework shows high potential for adaptable simulations in simulation-as-a-service applications. The subservice for liquid handling based on robot configuration shows good results. In the future, the framework's evaluation has to be extended to other production systems. Additionally, a fully automated setup of virtual environments and an improvement of the subservice for liquid handling is considered. Thank you very much for your attention.
Thank you very much to Stephan Wein from the Machine Tool Laboratory of WZL Aachen, Germany, for sending us this video. For those of you who has just turned in on the live stream, we stream on from today to Friday the CIRPe Global Web Conference on 2 live streams. One of them is on this channel and the other one is on another channel. You can find the link just below to this video. And if you would like to post the conference on any social media, please use the hashtag CIRPe. This online conference is scheduled as follows: that we have a video, after each video presentation, a live discussion with the presenting author. And for the last paper, which is entitled Simulation Framework for Virtual Robot Programming in Reconfigurable Production Systems, we have our presenting author, Stephan Wein, on the telephone now. Stephan, can you hear me now?
Yeah, hello, Stephan Wein here. Thank you. Nice to be here.
Nice to see you again. So, so there is one question regarding your paper about the boundaries of the of your approach of the framework for real-world applications. Could you detail on that, please?
Yeah, thank you very much for the question. So first of all, this concept is demonstrated currently in the production system we also mentioned in our paper, the ICER factory. So it's a system for cultivating iPS cells, so stem cells. And we currently implement this framework to this production system and try to really make it work. First of all, we have this. We have 2 parts, so 2 main parts. This is the one from the sensors, which need to be integrated. This is working. Also, the simulation is working. And now, where's the border between having a real system and a simulated system? So only with CAD models. This is where we have some divergences. So it's not the same. We have some issues regarding the correctness of CAD models, of course. But if we say, okay, we have CAD models which have which are correct or which are optimally made up and have a good set of the geometries, we can really have make this system run, and we have not that much divergences between those. But there are 2 things. First of all, we need to match the CAD model and the real boundaries again by having a reference measurement. So we measure the reference distance or vector between a code, so this is a data matrix code, which is on every module and on a position where the interaction between robot and the module takes place. And by doing this, we can really set a really good configuration of the virtual environment, and this works out really well till now.
Okay, sounds great. And for positioning and also for further measurements, do you use any CIRP data, or what do you use for your approach?
So we thank you again for the question. So we first of all we use the camera data, but also we have integrated another sensor which is based on kind of laser measurement, doing a position, so just a relative positioning measurement. So we have the absolute positioning measurement done by the camera. So we have two cameras which are just scanning the working space, and on the other side we have the two sensors for every module which does scan the relative position. And so what we can show by this is that we can just add new sensors to it, and we can do a data fusion. So we just use the basic absolute data coming from our cameras, and we just add the relative position coming from the sensors. Also, we have tried to use some other sensors like acceleration sensors to measure slight position changes of objects. And this data can also be included there. Mm-hmm. And all this data comes to this data management system where we have these active asset administration cells, which just put the data together to a new data set, which is done by rules which are implemented. And afterwards, the service, like the simulation service, can just be automatically enabled. Sorry. Yeah.
Mm-hmm. Okay, thank you for your answer. There's another upcoming question. If you have any benchmark to other approaches in a similar with a similar data or data set.
So we currently the first benchmark we had was this production cell, but we are planning to do so in the next step, because we want to find out where are the boundaries of this full concept, and also where we need to adapt our framework in order to make it able to run for every kind of production cell. Currently, we are able to just put in new modules, of course, but also other robots into this cell. And it's just defined by the CID model we have from the different objects and also the cell itself. We can just put in any kind of other cell too, but we need to really verify it now. Yeah. I
see. Thank you for your answers, Stephan. Have a nice afternoon and talk to you soon. Bye.
Thank you, and same to you too. Bye.
Bye. So we are back on live stream too for the CIRPe Global Web Conference 2019. Our session is entitled Automation, Planning and Configuration, and we have two remaining papers today. So the next paper is from our colleagues from the Karlsruhe Institute of Technology from Germany, and the authors are